All right, so there are 3.8 million square miles in the United States. What if you wanted to know what that was like? You might plop down in the middle and just start exploring. And if you did that, this is what you'd see. Around 10% of our country looks like this. And just from exploring that 10%, you might think the world's flat, it's grassy, there aren't many trees. But now imagine instead you could increase your exploration by an order of magnitude. Instead of a few 100,000 square miles, you could do a few million and you could explore the whole US. And you'd experience this cacophony of sights. All of a sudden, your picture of the world is completely different and your understanding of nature has fundamentally changed. It's with this same spirit that physicists have undertaken the exploration of what we call the energy frontier. The energy here refers to the tools we use to explore. Essentially, how energetic is the probe that we bounce off the universe to learn its properties? The higher energy the probe, the higher precision we get, and every few orders of magnitude, we develop an entirely new understanding of how the universe works. Today, this work is done at colliders. High-energy particles are smashed together at incredible speeds, revealing the internal workings at scales smaller than an atom, smaller than even protons, and we can use the energy in these collisions to create entirely new forms of matter. And from that, we discovered a plethora of other particles. We call this collection of known particles the Standard Model, and we've been building it for the last century or so, and finally claimed completion with the discovery of the Higgs boson at the Large Hadron Collider in 2012. But that completion is decidedly an overstatement. While the model is self-consistent and has continuously shown to be accurate by experiment after experiment, it is clearly missing explanations for phenomena in our universe. Most notably, it has no explanation for gravity and no explanation for the dark matter that we see in our universe. So far, we've made colliders using stable charged particles. So electron colliders, for example, annihilate electrons with their antiparticles, creating entirely different particles with these super clean detector signatures, where you can easily see what happened in the collision and extrapolate backwards to understand the interactions that were at its core. You can do a similar thing with protons, which have the advantage of being able to reach higher energies. But because a proton isn't a fundamental particle, you collide the fundamental particles inside of the proton, and you get these messy decays with tons of stuff going on, which are a real challenge to work with and to understand the details of what's actually happening. But for our next machine, we're thinking of using a completely new particle, a muon, which is a heavier cousin of the electron, which might give us the best of both worlds. High energies, but also the opportunity to annihilate a fundamental particle with its antiparticle to harness its full energy and make something new. Today, the leader in the energy frontier exploration is the Large Hadron Collider. It's a proton collider, and you can see it here straddling the Swiss-French border. It's 27 kilometers in length and 100 meters below the surface. And it looks like this, the thing you can see in the top right, full of incredibly complex magnet systems that guide its beams. And where the particles collide, massive detector caverns have been excavated. This is a famous picture of the Atlas detector, which is actually missing the detector, and you can see why it's more famous than my unfortunate selfie with the detector inside of it on the right over there. Okay, so what happens if we want to take this strategy that we're working with and keep going to a new order of magnitude? If we're using the same strategy as the LHC, we'd need a 90-kilometer tunnel filled with more complex magnets than we've ever built. And this is what it would look like here in Knoxville. It would stretch all the way to Farragut. Meanwhile, if we started using muons to collide, it would shrink this footprint dramatically, using a collider even smaller than the Large Hadron Collider, that's the smaller purple circle, to reach our next steps, which means cheaper, less energy, less land needed, and that sounds great, right? But there is a problem. The problem is that a muon lives only 2 millionths of a second. But a cool thing happens when you make something go really fast. Special relativity kicks in, and just like an astronaut speeding through space in your favorite sci-fi movie, time slows down and they live longer. So the whole game with a muon collider is to make as many muons as you can and speed them up as fast as possible, and then they don't immediately decay and you can actually do something with them. And to that, you need a whole complex that looks like this. You create the muons, you wrangle them into a beam, you collide them, and every stage of this is extremely technically challenging. Plus, we have a new kind of challenge when we try to look at these collisions, different from what we saw in protons or electrons. We have our nice clean annihilation, but we also have to deal with the remnants of this constantly decaying beam barraging our detector, which is tough. But if we can figure out how to build this machine and how to do physics with it, we think we can use it to understand some of the most pressing questions about the universe. So this is an image showing dark matter in our universe, and for decades, we've known that this mysterious stuff is actually most of the matter in our universe, but we've never understood what it's made up of. A collider like this could answer that question. It could also tell us something completely new about the birth of the universe, how the Higgs boson and its interaction with other particles may have evolved through the first instance of existence, leading to what we see today, all of the particles in the Standard Model. And with this kind of possibility, there are, of course, a lot of people interested in this challenging endeavor, interested in doing something big and new. And this is a meeting that I organized at Fermilab, which is a possible host for a machine like this. And it drew a lot of attention. We even had a sitting congressman come talk with us about the possibility. That's the picture on the right. And this is a wonderful start, but a project of this scale doesn't just need physicists and funders. Building a muon collider requires a massive interdisciplinary effort spanning energy, the environment, international relations, local and national economics, and maybe it could include you. Thank you.